So our goal is to, in the first part of today's lesson, just apply our understanding of properties of exponents to make some comparisons. And then in the second part of today's lesson, we are going to add, subtract, and multiply polynomials. That is what we are doing today. That again is another application really of our properties of exponents. So that is what we are doing today in class. So without any further ado, here's example 3. And we'll read it together, a beach ball problem. It says the radius of a beach ball is about 5.6 times greater than the radius of a baseball. True story. How many times as great as the baseball's volume is the beach ball's volume? So here we see our first application, or one of our applications rather, for properties of exponents, where we can compare volumes. You see that they follow our very similar 3-step approach. Step 1, we got to decide what our variable is going to represent. We set up a verbal model, and then we solve using some algebra. So we're going to compare the volume of a beach ball to the volume of a baseball. These problems, so common on like the SATs and things of that nature, standardized tests. You see them all the time. But here's the problem, students who are really worried about time on the SAT will pick 5.6. It'll be an answer. True. It'll be one of the answers that you'll have to pick from. And they just rushing through. I'm like, oh, the radius is 5.6. The volume's difference is going to be 5.6 as well. But that's not the case. You're going to see that when we change that small linear measurement, it's going to change something that's squared or cubed by quite a considerable amount more. My husband and I had a discussion, quote unquote, a couple days ago about this very same topic because he was like, well, I'll get into it after I do the problem. But it's a common misconception that if you change the radius by, 5.6 times the original amount, that the volume would change accordingly, and that's not the case. You're going to see it changes by quite a bit more. So let's do it. In our solution, we're going to let r equal the radius of the baseball. And what they say here is that the radius of a beach ball is actually about 5.6 times greater than the radius of that baseball. Well, if you consider the idea that the volume of a sphere in general is found by doing 4/3 pi r cubed, we can compare our volumes by, inputting the different radii into the formula for volume. So you'll see here we have the beach ball's volume and the baseball's volume. That's our verbal model. So step 1, we identified our variable. Step 2, we write a verbal model. Notice they have beach ball on top, baseball on the bottom, because we're looking for a comparison. In the question it says, compare how many times greater the beach ball's volume is to the baseball's volume. If you flipped it, baseball on top of beach ball, you wouldn't get how many times greater. You get like a fraction, essentially because a baseball is smaller than a beach ball. So in this case, we have to put the bigger item up on top. You'll see there's a blank there. See it? Notice we're comparing the two volumes. So we have the volume of the baseball on the bottom, and that was just 4/3 pi r cubed, because r in this problem just represents the radius of the baseball. Now we have to tweak the radius of a beach ball just a little bit and input that into the formula for the volume of the beach ball up here. So we have 4/3 pi blank cubed. This is a cubed up there. It's kind of hard to see. Any ideas as to what goes in that box? Calvin. Yes, very good. Why, Calvin? Yes. Well, not the volume. The the radius. Yeah. So you see what I circled up here? 5.6 times greater than the radius of a baseball. So you take 5.6 times r and you put it in. And now we can use our properties of exponents to help us out. You'll see here that in the next step down, they cancel out the 4/3 pi. That's because 4/3 pi over 4/3 pi is just 1, so that reduces right out of the problem. And then we basically have left over 5.6, and that quantity, or 5.6r rather, that quantity is cubed. So we can use our power of a product property to distribute that exponent into the parentheses. Notice there's also no plus or minus. So we're also allowed to distribute that cube in there. And now what they say is, hey, you could think about this now. You have r cubed, r cubed. You could use your quotient of powers property. So we have 5.6 cubed, and then we could subtract our exponents. We have r cubed over r cubed, so you could do 3 minus 3. Subtract your exponents there. And then what you'll notice is that 3 minus 3 is just 0. And we talked about the 0 exponent property. You have r raised to the power of nothing. R raised to the power of nothing is just 1. So actually, you're going to take 5.6 cubed and multiply it by 1. You throw that in your calculator. 5.6 cubed. What'd you get, Calvin? Is he? Yeah. So about 175.6. Again, this is just a different way to do the problem. You could have canceled the r cubes too, but I wanted to show you that it just follows along with our properties of exponents as to why those r cubes go away. So it's just another application of our properties of exponents. We're not quite done yet though, because when we finish a word problem, you write your answer as a sentence. So it's safe to say that the volume of a beach ball is about 175.6 times as great as the volume of the baseball. So just tweaking our radius changed the volume by 175.6 times. So back to the discussion that I had with my husband a couple days ago. So, the holidays are coming and there's talk, we have some gift cards to Toys R Us and stuff like that we haven't used from birthdays past, and I want to get a trampoline. I think that'd be fun, but they're dangerous. It's probably an insurance claim waiting to happen. But here's the discussion we had. He's like, all right, well, if you want a trampoline, the 12-foot one is on sale for, I think it was like $180. But then there's the 14-foot one. So changes the diameter by 2 feet. The 14-foot one is on sale for like $250. So $70 price difference. It's like, that's a pretty hefty price difference for 2 feet. I was like, well, yeah, that's a change in the diameter, but how does it change the area? That's a ton more jumping space. My kid might not fall off the trampoline in that case. $70 well spent. So, it was an interesting discussion because that is a really common misconception. Changing that linear measure of that radius. People think, oh, it changes the area, a little bit. No. That's a difference, a measurable difference. Lots more jumping space. So it's just funny that I'm now teaching you guys about this. Look, we tweaked the radius by 5.6 times as much, and it blew up the volume to be 176 times the size. So maybe you'll learn your lesson. I think I'm going to lose, by the way. I don't know that we'll be getting a 14-foot trampoline. It would be a monstrosity. What's that? Well, they come with that now. I think that's standard. I think that was like a big safety recall back in the day. And I don't think you can, they don't have like back in my day, you know, they had the springs. You could like, your foot would just go like right through, you know. They like cover that now. I think there's been quite a few injuries. So yeah, I think I'm going to lose, but it is what it is. Okay, questions about that? In a few minutes, you're going to get a little bit more practice with your properties of exponents. But before I have you come back and do this independent practice, we're going to add, subtract, and multiply some polynomials together. So let's do that. Next page. So again, you could apply our properties of exponents to simplify or do operations with polynomials. So we're going to add, subtract, and multiply. I have a festive little background on this one. Lets me know I'm like a couple days maybe ahead of where I was the last time I taught this lesson. But then again, like we came back to school this year before Labor Day, so I think I'm like right on where we should be. Kind of works out. In example 1 here, we're asked to add polynomials together. I could probably teach this in 3 words. Combine like terms. That is what I'm going to show you again how to do today. That's essentially the gist of adding and subtracting polynomials. There are 2 ways to set up these problems. You get to pick by the end of the lesson today which method you like better. You could do these problems, you know, old school addition way, and you see I have a little sample on the marker board here. You know, back in the day when you folks learned addition, if you had to take 4,782 and add it to 1,384, you put those 2 numbers on top of each other and then added, you know, your ones place, tens place, hundreds place, thousands place, so on and so forth. That's what we're going to do with polynomials today too. That's one way. You can also, however, orient the problem horizontally and get to a satisfactory answer. So I'm going to show you how to add and subtract polynomials in 2 different ways. You could pick. At the end of the lesson today, I kind of want to see what you like best. So I have you doing an exit ticket also, and you're going to tell me like, oh, I like doing these problems vertically. I like doing these problems horizontally, and then you got to tell me why. So I just kind of, as we do these problems, I want you to really think about which way you like better. So let's do that. In example 1, you see that first thing my eyeballs see is that these are all written in standard form. So you want to write your polynomials in standard form first. It saves you a lot of grief in the end. Because if your polynomials are written in standard form initially, then your answer will also be written in standard form when you're done. Okay, wait. What's standard form? Let's review that real quick just to make sure. Go ahead, Ryan. Yes, very good. So we start with our largest exponent, work our way down. So I see I have 3x cubed minus 2x squared plus 4x minus 6. So my exponents go 3, 2, 1, and then there is an x to the 0th power attached to 6. X to the power of nothing is 1, and that is attached to 6. So that's why that's always at the end. And then I look in the bottom here, I have 1x cubed, and then 3, 2, there's no x's there, so some books will actually put in a placeholder there, 0 x's, and then add 3 to that. You could also just leave a space. Notice this puts like term under like term. So now I can just add. I have 3x cubed and 1x cubed. That makes 4x cubed. Negative 2x squared and negative 5x squared. That's just negative 7x squared. 4x and no x, that's 4x. Negative 6 plus 3 is negative 3. And notice my answer is in standard form. Not too bad. You could, however, you know, orient the problem horizontally if you like. So if you see a problem that's written like part B, the first thing you want to check is to make sure that they're written in standard form. So I have 2y to the third plus 7y squared minus 6y, and it goes 3 to y to the first, so that's in standard form. And then the second polynomial goes 2, 1, and then y to the power of 0. So that second polynomial is also written in standard form. Bless you, Eric. Now what I'm going to do is I'm going to combine my like terms. Essentially, I'm going to start with the degree holding power, which in this case is this 2y cubed right here. That's my thing that has the highest exponent in the problem. And that's where I'm going to start combining my like terms. So I see that 2y cubed is sort of my degree holding term in the first polynomial. And I'm going to see if there's any other y cubes that I could combine with that. And I don't see any. And then I see the next power down is 7y squared. Oops, I meant to do that in a different color. So I can add that to 7y squared. And I do notice that 7y squared does have a buddy in the next polynomial. It pairs up with negative 4y squared. And then I see I have a negative 6y, and I can buddy that up with the 3y in the second polynomial. And then at the very end, I'm going to look for any constants. And I don't see any in the first one, but I do see a constant in the second polynomial, a minus 9. And then I just combine them. Notice because everything was in standard form to begin with, my answer will be in standard form at the end. So essentially what I see here is 2y cubed, 7y squared and negative 4y squared is plus 3y squared. And then I have minus 3y minus 9. And that's that. Other questions about that? Maybe you're starting to think about which method you like a little bit better. Let's subtract. Again, subtraction is not really something I do with polynomials, although it says to subtract. Whenever I subtract polynomials, I always add the opposite. Essentially distributing the minus sign into the second polynomial. So in part A, you see that the problem is initially set up vertically. One polynomial is on top of the other. And then I look at the exponents, and they do go in decreasing order. Ooh, and there's a typo. This little 3 right here should be a 2. That second term in the second polynomial should be 3x squared. Did you fix that? Sorry about that. But I do see, since I'm looking ahead, that these were in standard form. So now what I could do, the goal is to drop the parentheses to be able to combine everything together. So I'm going to distribute this negative into that second polynomial. So I'm going to subtract 6x cubed, subtract 3x squared, add 7x, and subtract 5. Essentially adding these things together. So notice I didn't write the parentheses down. That's kind of the idea in distributing that negative in, so that you could just combine everything. And now it's very much like what we just did. Just add them up. So I have a 7x cubed and negative 6x cubed. That's 1x cubed. I have negative 9x squared. I have positive 4x and plus 2. You can, however, orient the subtraction horizontally, distributing the negative in, and how you would do that, and then adding. So we're going to take 12x squared away. We're going to add 9x, however, and we would add 3. And then you kind of rearrange it. Everything's written in standard form. So you kind of rearrange it so that your like terms are sort of buddied up. So you're going to buddy up the x squared, or I'm sorry, the 8x squared, and the negative 12x squared. And then you're going to buddy up the negative 5x and the positive 9x, because they're like terms. And then the positive 11 and the positive 3. And then combine. So 8x squared, take away 12x squared. That's negative 4x squared. Negative 5x and 9x is 4x. Whoop. And 11x, or I'm sorry, 11 and 3 is 14. And you see that I was crossing off things just to make sure I didn't leave anything out. It's a little tip for you. It'll help you out. All right, so let's make sure you can add and subtract. These problems are set up horizontally, but you can set them up with any method you like. Maybe it's a good chance now to experiment with one or the other to see what you like. So yeah, I'll go ahead and give you a minute to do these two problems, and I'm going to start checking your homework from last. Saying plus AT. Yeah, I think you're right. Yep, good job. Sorry, I didn't mean to scare you. I just couldn't hear you. It's all those trombone lessons in my basement. Yeah. Calvin. Minus, I'm so sorry. Again, minus what?
13.
Oh, thanks for speaking up. That's kind.
Minus 2.
Thanks. Well, that's right. Good job. Okay, questions for Calvin or myself? Okay, so we've added and subtracted. Last bit, multiply. So we're going to multiply polynomials together. The first example of this comes at us as a binomial times a trinomial. And basically, I'm just going to do a very organized process of the distributive property, or very organized version of the distributive property. The first thing I'm going to do, check to make sure everything's in standard form. So if I'm in standard form to begin with, that's a little less legwork I have to do at the very end. And then, I see that I am, I can distribute x into the parentheses, and then, in a different color, I'm going to distribute negative 3 into the parentheses. Notice I said negative 3. I'm going to pull that sign in with it. So distributing x in, I have x times x squared. Thinking back to what we just talked about at the beginning of class today, when you have x times x squared, you're allowed to add those exponents together. So that's where you get your x cubed. And then we have x times 2x, that's plus 2x squared. And x times negative 5 is negative 5x. And then I'll go ahead and distribute my negative 3 in. So I have negative 3x squared minus 6x plus 15. And then you can add them up. Notice when I distributed the negative 3 in, I did just put the negative 3x squared underneath the 2x squared to do the addition in the vertical fashion that we just talked about. Again, you can do it horizontally if you like. I just think it's a little easier to do it this way. So I have x cubed plus nothing. That's just x cubed. 2x squared, take away 3x squared, that's minus 1x squared. Negative 5x and negative 6x put together is negative 11x. And 15 and nothing is 15. So that is that. Now, when I multiply 3 binomials together, I want it to look like a binomial times a trinomial. I want it to look like the previous example. Well, in order to do that, what do I do first all the time? See these back two binomials? I FOIL these first. So step 1, I'm going to FOIL x plus 7 and x plus 1. And then it'll look like the previous example. So I bring down my x minus 3. And then I do FOIL my x and x, so I get x squared. Outers is x times 1, which is 1x. Inners is 7x, so put those together, that makes 8x. 1x and 7x is 8x, and then I have 7 times 1, which is 7. So now it looks like the previous problem. Even down to the x minus 3 is the same. So again, I'm kind of going to execute the same steps. I'll distribute my x in, and then I will distribute my negative 3 into those parentheses. So distributing an x in, x times x squared, that is x cubed. X times 8x is 8x squared. And then x times 7 is 7x. Now distribute a negative 3 in, so I get negative 3x squared minus 24x, and then minus 21. Combine my like terms. I get x cubed plus 5x squared minus 17x minus 21. And that's your answer. Notice when you have three binomials where the first term is x, my final answer begins with x cubed, because at some point I had to take x times x times x. So I can use that as a gauge to make sure it's accurate. So now, you have two sets of independent practice problems to work on while I finish checking off a little bit of homework. You have this last independent practice problem, and then you might notice that we still have to go back and make sure our properties of exponent look the way they're supposed to. You have that independent practice in your note packet as well. It came out a lot cleaner on your copy than it did in my slideshow today. But this will get us through, I think.